All right, another video about gases. So we're going to talk about what's called the kinetic molecular theory. Kinetic, motion, action, molecules, theory. This is what we think they do. So this is how we think molecules move, period. So what we're going to say is that in the KMT, we're going to say that gases are moving constant. They don't ever stop. They're always moving around. And we say that they're in random motion. So they don't have an agenda. This gas is going to be moving, boom, hits and bounces off. Period. That's what happens. It hits another one, boom, it bounces off. We say that they go in straight lines until collision. So we say that gases move, hit, and bounce off. 3, we say that they are perfect elastic collisions. This is something we say gases do. Imagine if I take a bouncy ball, drop it, boom, 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 boom. I'll do it 42 more times. Boom, boom, just kidding. If it was perfectly elastic, that means that the ball would just never lose energy due to friction. In a real world, we say it goes boom, 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 boom. It lost energy because of friction. So we say they're perfectly elastic collisions, which means that the gas particles are hitting the walls, but they're not losing energy to the walls. Now they might transfer energy. You might get particles that come by, this guy's moving, and they hit, and this guy moves fast and this guy moves slow. You might get things like that, but the collisions are still perfectly elastic. We're not losing energy due to heat. We could say number 4, that the average kinetic energy is directly proportional to temperature. So, and we could say temperature is a measure of the average kinetic energy of a sample. And so one of my favorite graphs of all times, you guys who have me know this, are graphs that look like that. Love graphs that look like that. And so if I say, hey, this is the temperature of a sample, this is the temperature of a sample, so this is energy, this is not the temperature sample, this is a sample of gas at a certain temperature. This is energy here. This is energy here, and these are just numbers of particles here. So that's energy on that side. Well, we can see that, the average is going to be somewhere around there. There's our temperature. But in any given sample, there might be some that are moving crazy fast, and there might be some moving very slowly. But so this is an average. So whenever we look at temperature, don't think it's just the kinetic energy of a sample. Not all particles are moving the same. It's the average kinetic energy of a sample. And one way to remember that is kind of remember that if you have yourself some water here, and I know this is water, but you'll get the idea. If this is water here, it has a certain temperature of the water. And since water is moving around on an average kinetic energy, but that means that there are some particles over here at this interface with the air that are moving fast enough to be able to break free. Not all of them. Some of them are really slow, some are moving fast, but some are on the end over here that are fast enough to break free. So that's the average kinetic energy of a sample.